Good morning, everybody.
Good morning.
Hope you're having a nice Saturday morning. It's October 21st. And last time we saw the evolution of heat engines, or steam engines, as it were. And we saw how Captain Savory's old miner's friend and Thomas Newcomen's atmospheric engine eventually led to James Watt and his steam engine. A lot more complicated, a lot more efficient, and how that fueled the Industrial Revolution. We also witnessed how the evolution of the understanding of heat changed. And we went from heat as some elastic fluid. We saw caloric as the substance of heat, and how Sadi Carnot used that idea to show how steam engines or heat engines are actually fueled not by the consumption of caloric, but simply by the flow of caloric from hot to cold, or so he thought. But then we saw that as time went on, this notion of caloric as a real material substance really became untenable. We saw how Count Rumford showed that in principle you can produce unlimited amounts of heat simply by boring a cannon with a blunt borer. Now obviously that already gives some tension with the idea of there being some substance if you suddenly can produce an unlimited quantity of that substance. And then later on, around 50 years later, James Joule showed that not only can you produce unlimited quantities of that caloric, or of heat, but actually you produce a very precise amount of it. For a certain amount of mechanical energy that you expend, you get a certain quantity of heat. And it's always the exact same quantity of heat, irrespective of how you decide to generate it. He used his paddle wheels to generate friction in water, or he went through electricity and then used electricity to heat the water. And every single time, he measured exactly the same quantity of heat. So that was really, the death blow to the theory of caloric. Now, but that also meant in this day, 1850, and that's part of why his results were so convincing, electricity was pretty commonplace. In his paper, he just writes sort of off the cuff that he's using electricity to do this and that, which means that today we should really understand how people got that far. So where did electricity come from, and what is the nature of electricity? And what was the understanding that James Joule himself had about the nature of electricity that he used in his experiments? So once more, if we really want to get the context, we need to go all the way back to ancient Greece. Now this time not to Alexandria as we had done with the science of heat, but to mainland Greece, to Athens in fact, to the city-state of Athens, where the great philosopher Plato had a school. So here's Athens, here's the city wall of Athens, and here is the academy, run by Plato. Now this wasn't an academy in the sense of a school with teachers and students and a fixed curriculum. This was more a place of a debate. You see, it was primarily upper-class men who participated. It was a place to debate, to put out ideas and to have them debated, to make new ideas happen and so forth. And one of the students there, or one of the participants, I should say, in the discussions was Theophrastus. He came to Athens as a young person and then participated in that discourse. And he was a person who wrote about the entirety of contemporary knowledge at that time. He was a botanist, and in fact he wrote the book, Enquiry into Plants, that made him the father of botany, because he was the person who started this classification into different species of plants and sort of interrelations between them that very much still has a place in this field today. Now he also wrote a book about minerals, and he also classified minerals. If you will, you open the book and then you have section upon section upon section describing all the different minerals that could be found in the then known world, which was centered on Greece. Now actually, if you're wondering, Theophrastus is not his real name. This is actually a nickname that was given to him by Aristotle, who he would have met at the school there. So Theos is God. So Theophrastus means godly phrased, which is Aristotle's name for him, which stuck because he was extremely eloquent in his discussions, and he would, be a fierce opponent in a debate. So here's what he wrote about stones, and one aspect in particular is the starting point in our journey into the nature of electricity. In this book on stones, 300 BC, he writes, "Amber has the power of attraction, and some say that it not only attracts straws and bits of wood, but also copper and iron if the pieces are thin." Now amber, here's a picture of it. The Greek word for it is electron, which already gives you some hint that this is really the root of what we have today, the word for electricity. Now actually, There are some speculations that even the Greeks didn't invent this word, they took it from the Phoenicians, where it meant shining light. So actually, it sounds like this word electron doesn't really refer to the fact that amber attracts things. It refers to the fact that it appears translucent if you put it behind the sun. So anyways, this attraction that he was mentioning is of course the exact same attraction that you can feel on your head, on your hair, if you rub a balloon against them. This is what he was writing about. This is something that struck people. No other stone did that, but amber did. Today we would call that static electricity. Now he also writes about another stone that has similar powers, and that is lodestone or magnetite. Here is a picture. The stone that attracts iron is the most remarkable and conspicuous example. This also is rare and occurs in few places. This stone too should be listed in having a similar power as the one that amber has in attracting objects and quantities. So this is the first place in history that the long and lasting for centuries and actually millennia connection between electricity in amber and magnetism in magnetite starts. As we're going to see throughout today and the next lecture, this connection between electricity and magnetism is going to continue all the way up to the present age. Now, Theophrastus was content simply describing the phenomena that he observed and classifying everything that he saw, amber, lodestone, magnetism, electricity, but other people, among them Plato, tried to understand what the reason was for this magical power. And Plato simply attributed it to the gods. So here's what he writes. There is a divinity contained in the stone, which Euripides calls a magnet. He speaks about magnetite or lodestone. This stone not only attracts iron rings, but also imparts to them a similar power of attracting other rings. And sometimes you may see a number of pieces of iron and rings suspended from one another so as to form quite a long chain. Okay, here is a modern picture. You take a piece of magnetite and a piece of paper clips and things attract. But not only the paper clips attract to the magnetite, but then down here, one paper clip is attracted to the next paper clip. So he attributed there being some living being, some divinity inherent in the stone that would give similar powers to things it came into contact with. And in fact, this is a mineral that's quite unlike any other. Normally stones are dead and just passive, but this object, this stone here, is quite striking. And so all of them derive ultimately their power of suspension from the original stone. This is where the source of all of this phenomena lies. And in fact, magnetism was very quick to take off, much faster than electricity, in fact, in navigation. People understood very quickly that there is some interaction between a piece of magnetite and the Earth. And in fact, the Chinese, in the Han Dynasty, 200 BC, built lodestone compasses. Okay, something like this. You take a piece of lodestone and you shape it such that it can freely rotate if you put it on a flat plate of metal here. And then the Chinese name for this, translated, means a south-pointing fish, because this object here would just rotate until it points in the north-south direction. This was one of the first compasses. Now, before it was used for navigation, it was actually used for divinations and making prophecies. You can see all of this writing around here was a means of deciphering the message, if you will, that the lodestone gave you. Now, magnetism and the compass also came to Europe at around the 1200s, where a French mathematician, this is the first recorded occurrence of that, a French mathematician, Pierre de Maricourt, for some reason, he'd found himself joining the French army, besieging an Italian town of Lucera. And so he sits there in the trenches of Lucera and he writes a letter to a friend at home. And in this letter, which is quite comprehensive and quite long, he outlines in great detail how to build a compass using a lodestone. And he is very clear to emphasize that even though the stone be moved 1,000 times away from its position, it will return there to 1,000 times as by natural instinct. So people were recognizing the power of magnetism that seemed still very mysterious to them, but they didn't understand it. Now, the first person to study this in great detail around the same time, in the late 1500s, was William Gilbert in Britain. He was a physician, and in fact, he was the personal physician to Queen Elizabeth I, and then to King James V and King James VI after she passed away. And he, besides being a physician, played with magnets, and he did experiments about magnetism. And in fact, here's a painting of him demonstrating some of his experiments to the Queen, who is set there. Now, the book that he is most well known for is this one, published in 1600, on the magnet and magnetic bodies, and on that great magnet, the Earth. Okay, so here in the title, he already puts up front his big discovery, which is the reason why compasses work, which is that the Earth itself is like a giant magnet. And so the little magnet that is the compass needle and the big magnet that is the Earth, they sort of conspire to then make the magnetite needle align itself with the north-south. Before he understood that, it was not obvious. There was a time when people thought it was the North Star that attracted the needle, or there is a giant magnetic island near the North Pole that attracted the needle. In fact, it was the Earth, as Gilbert pointed out. Now, Gilbert also wrote about electricity and about amber, and he tried to understand a mechanism, similar as he had done for magnets, what is behind this attraction of amber. So he writes, or he asks himself, now, what is that produces the movement? He's referring to the movement of bodies being attracted to the amber like the woman's hair was attracted to the balloon before. So here's the amber, and he uses a feather as the body that feels the attraction. But he says, what is behind this? Is there something imperceptible for us flowing out of the substance into the ambient air? Okay, he's trying to invent the mechanism. And if it is an effluvium, does the effluvium set the air in current, and is the current then followed by the bodies? Okay, imagine if the amber is sort of rubbed against your hair and it attracts things, is it because it generates some wind in the air around it, and that wind is it that picks up the feather and sort of attracts it to the amber? But he says that cannot be the case, because an amber that will attract bodies from a considerable radius will cause no motion to a candle flame. So if it was really some wind or motion in the air, then if I put it close to a candle flame, surely the candle flame would also notice the wind, but it doesn't. So what else is it? Or is it the bodies themselves directly that are drawn up? If it's not the air around them, the bodies themselves must feel in some way that attraction. But if so, then supposing that the surface of that body is clean and free of adhesions, what need is there of friction? So he thinks, well, if that wasn't a feather that's sort of rough and easy to pick up, what if this was a shining, polished object? How would that force that somehow picks it up be able to actually hold on to it if the surface was very, very polished? What need is there of friction? And then he is very confused because he says, for as no action can be preformed by matter, save by contact, these electric bodies do not appear to touch, but of necessity something is given out from the one to the other. So he says, something surely must be happening around that amber to pick up the feather, and I don't know what it is, but I know for sure that something is coming out of that amber, for how on earth would otherwise be the feather picked up? So that's the very first time that a spooky notion of an action at a distance without any perceptible mechanism behind it shows up. And as we'll see, many people after him will be spooked by that same thing. They're trying to invent something or trying to find the reason for what is it that ultimately picks up the feather. Nothing that we can see. And in fact, he pointed out something else, and that is that amber, which for the Greeks was godlike and contained the divine spirit, amber is not special at all. In fact, the same, referring to the attraction again, is done by many other objects: glass, diamond, sapphire, carbuncle, iris stones, opal, amethyst, English gem, beryl, rock crystal. So even normal glass, window glass, can do the exact same thing. If you rub it, it will attract bodies just like the amber did. Okay, so suddenly, that amber, which was singled out in the book on stones that Theophrastus wrote, now is just one among many. One among many bodies that can become electrical if you rub it. And so, this was the state of the art around 1600. It was very confusing, if you will. Previously, with amber being the special outlier, things were very easy. You could easily sort of make do with attributing everything special about amber to the identity of amber. But now, if it's just one among many, the need to understand what's really happening suddenly becomes a lot stronger. And that need is also what was felt by Francis Hauksbee, who was also in London at that time. Now, he was a draper at the beginning, as he grew up, which is a merchant of clothes and garments. but then he changed profession and became an instrument maker, a mathematical instrument maker, which, as you will remember from last time, also James Watt was. This is a profession that's very much in fashion in these days. So that's what he did. And he became noticed by Isaac Newton, who was at that point the president of the Royal Society of London for Improving Natural Knowledge. Today just known as the Royal Society. This is, if you will, the National Academy of Sciences in the United Kingdom today. Newton was its president, and he hired Francis Hauksbee as a demonstrator for experiments. So the way the society would operate is the members would get together and news will be read out, scientific news, sent to the society by scientists around the country and even sometimes abroad. Then the news would be read out, and then sometimes Hauksbee would come in and illustrate the news with some of his experiments that they would repeat or invent himself. And so by 1709, he had done enough experiments to write an entire book about them. He writes, "Physico-mechanical experiments on various subjects containing an account of several surprising phenomena touching light and electricity." An entire collection, if you will, of the phenomena that electrical bodies can exhibit. And so one of the first things he did was to, if you will, industrialize the rubbing of a body to generate electricity. So what he does is he puts up a glass sphere, a hollow glass sphere, on a spindle and connects it to this crank down here. So if you turn the crank, that glass globe would spin very, very rapidly. And then all you had to do is simply take a piece of cloth and push it against that rapidly spinning glass sphere, and it would get electrified much more strongly than it would otherwise do. And then he took this electrified glass sphere and did experiments on it. And one of the things he did is he built himself a wooden structure around that electrified glass sphere, and he attached woolen threads to that wooden structure. And once the ball was electrified, all of the woolen threads would come standing up, just like that woman's hair did before. He writes, "The woolen threads have been laid hold of by the effluvia. Then the glass had no motion at all," he stopped the spinning, "but they would keep standing up. All the threads continue in their straight, directed posture, pointing straight at the glass ball." And in fact, the same happened if we put the threads inside that hollow glass sphere. The threads here issued like rays from a center outwards. Again, they would be attracted to the glass sphere, just like the hair does here. In fact, he noticed also that with the situation like this, the threads standing erect, if he approached them with his finger, even though he doesn't touch the threads, they would start moving as his finger approached. The threads avoided the finger when it approached very near their extremities. Just trying to understand what's going on. And he says this reminds him, it very much resembles a solid, since motion may be given to a body by pushing the effluvia at some distance from it. Okay, so he coins that term of an electric spider web. He says what's really happening there is sort of invisible threads, spider threads, connecting the electrified glass sphere with all of those woolen threads. I have my electrical spider web. And so if I disturb that spider web by coming close to it with my finger, I will also, impart motion on all of the woolen threads around it. And in fact, he is very confident that he understands exactly what's going on. So here's his interpretation of that experiment. "I think it is too plain to be questioned that there is an emission of some matter consequent on the friction." Okay, these electrical spider threads are coming out of my glass sphere after I rub it, and that this matter emitted is also emitted from or by the tube, the glass sphere, I take it to be as plain as the former. So clearly the source of whatever's going on is the glass sphere. And I believe there is hardly anyone but will allow that this matter, if it came from the tube, were certainly reposed and lodged there before. Okay, so clearly he says, whatever is emitted by the tube, this effluvium of his, as a cause for these electrical spider threads connecting the woolen threads, must have been inside the glass before. And I'm just liberating it by rubbing the glass or spinning the glass ball and touching it with the cloth. So here's the first time that electricity, again, is given a material quantity. Just like with caloric from last time, electricity now is given some material existence. Something that was already there all along, and I'm just getting it out by rubbing the sphere. So Hauksbee was a man of strong convictions, as you could see. He was very clear and very sure of himself. Our next hero is exactly the opposite. Stephen Gray is a very humble and very straightforward person. He also started in the garment business. He was a cloth dyer, which was very hard manual labor. It involved contact with toxic chemicals and toxic colors. But he was also a hobby astronomer. His handicap was that he grew up in the town of Canterbury and didn't really have a way of getting in touch with the establishment of science. Now, to his luck, his brother at some point became the mayor of Canterbury, and through his brother he managed to get connections with the two big centers of learning in England at that time, which on the one hand was the Royal Astronomy at Greenwich, south of London, where this gentleman here, John Flamsteed, has just taken the helm as the Royal Astronomer in the UK. And the second was the Royal Society, where this gentleman here, John de Sagollet, had just taken over from Hauksbee as the curator of experiments and the master of experiments as they're being presented in the Society's meetings. Now, we are going to meet Stephen Gray towards the end of his life when he takes up pension in the Charterhouse, which back then was what we would call today simply an elderly care home. And he was a simple pensioner there, lodging a small room. Now, as we saw, the way that discoveries would be announced then was to write a letter to the secretary of the Royal Society. And also Stephen Gray made one of those discoveries, and he also wrote a letter to that society's secretary. And what I want to do now is actually read you some passages of that letter, because the way he writes not only makes it very clear what it was that he was discovering, which is very important, but also makes it very clear how he must have felt when he made this discovery, his childlike joy and his let's try everything kind of attitude at making that discovery. So here's what he did. I made several attempts before on the metals. He is trying to see whether they might not be made attractive by the same method as other bodies were, so by rubbing similar as glass and amber, but without success. And then he says, I then resolved to procure me a large flint glass tube to see if I could make any further discovery with it. Okay, so first trying something off the mainstream, trying to rub metals to see if they couldn't be made electrical, not succeeding. He then says, okay, fine, let me follow the mainstream of science, let me get myself a glass tube, let's see what happens then. So here's his glass tube, and it's a glass tube, as a glass tube is, it's hollow. And so what he does is he puts corks on both sides so as to prevent dust and dirt from getting into the tube. And then as a good scientist, he says, the first experiment that I made was to see if I could find any difference in the attraction of the tube when it was stopped at both ends by the corks. But I could perceive no sensible difference. So he takes his feather, he rubs the glass tube with the corks in, and he says the glass tube attracts just the same, irrespective of whether there are the corks in or not. But then he notes, but upon holding a down feather over against the flat end of the cork, which attracted many times together. So he noticed if he puts the feather over here, the cork also attracts, in fact, much stronger than the main glass tube does, at which I was very much surprised and concluded that there was certainly an attractive virtue communicated to the cork by the excited glass. So he says, well, I'm rubbing the glass and I'm clearly electrifying the glass as many people before me had seen, and that's why my feather gets attracted, but clearly I'm not rubbing the cork. So if the feather gets attracted to the cork at the end, the glass tube must have given something to the cork to make it attractive. And that was the starting point for him, and at this point there is no going back. And he continues. Having by me an ivory ball of about 1 inch diameter with a hole through it, this is what I fixed upon a first stick, about 4 inches long, thrusting the other end into the cork. So he's trying to see what else he can do. Puts the first stick, his ivory ball, into the cork, and he rubs the tube. And upon rubbing the tube, I found that the ball attracted the feather with more vigor than the cork had done. Okay, so he found that he could extend the cork through a wooden stick, and there is the ivory ball, and in fact the feather would still be attracted. So whatever the glass tube was communicating to the cork went through the first stick into the ivory ball, and then the ivory ball itself became attractive. And then he tried, everything else that you could do. I then fixed the ball on longer sticks, first upon one of 8 inches, and afterwards upon one of 24 inches, and found the effect the same. Then I made use of first iron and then brass wire to fix the ball on. Okay, here's the wire, here's the ball. He connects it instead of the wooden stuff. Inserting the other end of the wire into the cork, as before, and found the attraction was the same as when the first sticks were made use of. Okay, so it doesn't depend on them being wooden sticks or even first sticks. A piece of wire would do just the same. I then went on to see upon what other bodies the tube would have the same effect. Now, knowing that it doesn't really depend on what material he's using to transmit that electric virtue, he's trying to see what the bodies are that he could transmit it to, if you will. Beginning with the metals. This is what he started out doing but was unsuccessful. First, with small pieces, as with a shilling or a half penny. So he takes a stack of coins and he contacts them, and lo and behold, they would also get attractive. So he found that you could make metals electric not by rubbing them, but by bringing them in contact with something else that you had made electrical before through rubbing, in this case the glass tube. But then he continues with larger quantities of metal. And here you can really see him just going around his room and trying all the objects he can really find and get his hands on. He made use of a fire shovel, tongs, an iron poker, clearly from the fireplace in his small little room, a copper tea kettle, which succeeded the same, whether empty or full of either cold or hot water, a silver pint pot, all which were strongly electrical. Okay, irrespective of what he tried, all of his experimental subjects became electrical. And this was, if you will, his first big discovery. You can electrify metals, just not in the same way as other people had done by rubbing them, but simply by bringing them into contact with something electrical. Electricity can be transmitted and imparted on other objects. But he goes further. I next proceeded to try at what greater distances the electric virtue might be carried. How far can you push it? With several pieces of Spanish cane and fir sticks, I made a rod, which, together with the tube, was somewhat more than 18 feet long, which was the greatest length I could conveniently use in my chamber. You need to imagine him in his small little pension room in the elderly care house, trying to fit an 18-foot long wooden stick to try to do his experiments. And he found the attraction very nearly, if not altogether as strong, as when the ball was placed on shorter rods. So nothing was really getting weaker. Irrespective of how long he made the rod, the electricity would continue to go through. The feather would still be attracted. And thus far I proceeded before I went into the country. Okay, he goes and visits a countryside friend of his who lives out in the countryside, has a large mansion. Taking with me several glass canes and such other materials I thought would be necessary and could not well procure there. Okay, he had this trip planned for some time, and his experiment somehow happened just leading up to the trip, so he makes sure he takes all of his supplies with him because he wants to keep on playing. And so the sky is really the limit. May 31st, in the morning, to a pole of 18 feet, the one he brought, there was tied a line of 34 feet in length, so that the pole and line together were 52 feet. With the pole and tube, I stood up on the balcony, the assistant below in the court. Okay, here is he with the tube on the balcony, first floor, and then the assistant down on the ground. Then the tube, being excited as usual, rubbing it with a cloth, the electric virtue passed from the tube up the pole and down the line to the ivory ball. And lo and behold, the feather was attracted. Mr. Wheeler, who is the friend that he was visiting and at whose mansion he was staying, was desirous to try whether we could not carry the electric virtue horizontally. You see, thus far, they have really just done vertical transmission because that was easy to do, right? You didn't have to suspend or otherwise fix the wire to anything. But with horizontal transmission, that was more difficult. He proposed a silk line, Mr. Wheeler did, to support the line, by which the electric virtue was to pass. So here's what they did. By this time, they had moved into Mr. Wheeler's barn, where there's a lot of space. And so they put up some timber poles, and then they fixed some silk lines to connect them. And on top of those silk lines, they ran their line along which they tried to communicate the electricity. I told him about the silk. It might do well upon the account of its smallness. Silk wires is very, very small, so that there would be less virtue carried from the line of communication. Okay, so he thinks, because silk is really, really thin, the electricity that they want to transmit along the wire would continue, and very little of it would go through that tiny little cross-section of the silk. Their understanding is that the silk line hinders sort of the flow of electricity down the wooden poles because it's so thin. We'll see later that that's not true. We then proceeded farther. They managed to run one length of the barn and still have the feather attracted on the other end of the barn. they proceeded further by adding so much more line as would make a return on the other side of the barn. The whole length now being 293 feet. Okay, they go from one side of the barn all the way to the back and run the wire back to where they started. And though the line was much lengthened now, they found no perceivable difference in the attraction. And the feather was still attracted to the ivory ball. This encouraged us to add another return. Okay, they go back and forth once more. But upon beginning to rub the tube, our silk line broke, being not strong enough to bear the weight of all of the lines that they suspended on top. And so instead of silk, they used something that is more durable. They used brass wire, much stronger, and this supported the line of communication all right, but though the tube was well rubbed, there was not the least motion or attraction given by the ball. Okay, as soon as they replaced the silk with brass, which is a metal, the experiment no longer worked. And that was their crucial discovery, by which they were now convinced that the success that they've had before depended upon the lines supporting the line of communication being silk and not upon their being small, as before trial I imagined it might be. With the effluvia come to the wire that supports the line, okay, the brass or the silk, it passes by them to the timber to which either of them is fixed, and so goes no further towards in the line than to carry it to the iron ball. Okay, so they already understood this was the crucial insight that they didn't imagine was true before, that if you put brass wire here instead of silk, the electricity that is to continue back and forth along the line to reach the ivory ball was simply shorted out through that conductive brass wire. And so this told them that bodies communicate electricity, in fact, not in proportion to their physical size, as they previously imagined, that silk line being super, super thin, and that's why they thought, before doing that experiment, why they worked, but in fact, according to something entirely different, a new property of that material, which today we call the conductivity. And we call metals good conductors of electricity, and we call silk a bad conductor of electricity, but it has nothing whatsoever to do with the physical size of them. And note that how this is exactly the parallel to the story we've told a number of lectures ago with Joseph Black, when he found that mercury, despite being much heavier, heated up when placed next to the fire much quicker, which told them that mercury is less efficient at storing heat than water is, which is exactly the opposite of what you would expect if you think heat is stored according to the weight. Whereas here they imagined electricity is transmitted according to the diameter. In fact, it's not true. In fact, in both cases, a new quantity needs to be invented. In Joseph Black's case, it was the capacity of heat, and in Stephen Gray's case, it was conductivity. And of course, the magnitude of this discovery is really hard to overstate. They went from the first electrical transmission line to what we have today, exactly the same principle. You have a very well-conducting wire connecting your power plant to your city, and instead of a silk line, today we use ceramic to prevent the line from touching the pole from which it is suspended. So electricity can not only be generated, it can also be transmitted. But the nature of electricity still very much is a mystery. And while Stephen Gray was very much that kind of explorer who wants to try everything simply without thinking and just wants to have some fun, if you will, in retirement, our next hero, Charles Dufay in Paris, is exactly the opposite. He was the son of a high-ranking military official, and he was really brought up in a highly disciplined and rigorous way. Later on in his life, he became the superintendent of the botanical garden in Paris, which was then called the Garden of the King, and he totally turned it around from something that was sort of run down and not very attractive to something that was flourishing and highly connected with other botanical gardens in the rest of Europe. And what he also did, he was lured in by that promise of electricity, as so many others had done, and he was playing with electricity by himself at home. And as a member of the French Academy of Sciences, he did something very uncommon, which was to write to the English. He also sent a letter to the Royal Society in London announcing some extraordinary discoveries that he has made on the electricity of bodies. And that discovery came forth from a rigorous experimental program that he put himself through. You can sort of see his upbringing speaking to him, the discipline with which he proceeded. And he discovered some very simple principles, as he announced. First, he found that all the bodies, in fact, metallic, soft, or fluid ones, accepted, may be made electric. by first heating them more or less and then rubbing them on any sort of cloth. So he repeats what we already know, that it's not only amber that can be made electric, but also glass and many other substances, as he tried systematically. All kinds of stones, as well precious as common, all sorts of wood, and so on and so forth. But then he goes, second, I have found upon trial that all bodies, being fixed to a stand, and that set on a plate of glass or wax, may be made electrical, without exception now, whether solid or fluid, by making contact with the excited glass tube. So this is exactly what Stephen Gray had found. If you have a glass tube that you have electrified by rubbing it, and you put whatever objects you desire on a glass stand, so that could be well insulated, touching these objects with the excited glass tube would also impart some electricity onto these other objects. And he in fact points out that this is glass or wax is very important because one would try in vain using a platform made of wood or metal. So again, it's important that the material down here is the right one, otherwise the electricity would simply, flow to ground and not stay in the object we were trying to electrify. And that rule of things having to be placed on an insulating base became known as two-phase rule. Very important, and we'll see that come back and actually hit us. But then his most important discovery is the following. Chance has thrown in my way another principle, more universal and remarkable than the preceding one, we just talked about, which cast an entirely new light on the subject of electricity. He found, through a systematic study, the following. The principle that he discovered is the following, that there is two distinct electricities, very different from one another, one of which I call vitreous electricity, and the other one I call resonance electricity. Okay, the vitreous electricity is that of glass or precious stones, wool, and many other bodies. And the second, the resonance electricity, is that of amber, thread, paper, and a vast number of other substances. So now suddenly, he has this entire new kind of electricity, and he describes how they differ. He says the following. The characteristic of these two electricities is that a body of the vitreous electricity, for example, repels all such as are of the same electricity. Okay, if I electrify a glass and a precious stone, they would repel one another. And on the contrary, attracts all those of the resonance electricity. Okay, so if I electrify a glass tube and a piece of paper, they would attract. Now note that this is something nobody else has noticed before him, because nobody else had really gone through systematically and tried all of those different materials and made careful, reproducible experiments to try them out. And today, this classification is still very much in use. Today we call it the triboelectric series, and we rank different materials into positive and negative, which he called vitreous and resonance. Today we use different words. Glass is at the very top, and rubber and amber are at the very bottom. Okay, so the way to read this table is if you have a piece of glass and you rub it against rubber, the glass would get vitreously electrified and the rubber would get resonantly electrified, and so on and so forth. He set the groundwork for this classification of positive and negative materials. And so that was the state of the affair in around the 1740s. Electricity was very much a party trick in the courts of the kings and the living rooms of the wealthy. One of the experiments that would be shown off is what they call beatification. A person would be dressed up in a knight's armor with iron, lots of spiky metal sticking out, and then there's the glass sphere that's being turned and being electrified, and then the person on that wooden stool is being electrified, and out would come like little lightning rods out of the peaks of the metal armor that they were wearing. There was another demonstration that was called the electric kiss, where a young lady would be placed on top of an insulating stool, would again be electrified, and then somebody would be asked to give her a kiss, and then that person, of course, would be shocked. Even at Versailles, place of the French king, there would be little boys suspended from the ceiling on silk wires, would be electrified by a glass tube, which you can see here, and then there was a little table with paper shreds placed, and they would come swoop flying up into the boy's hand because they would be attracted. There was even another demonstration that would be called drawing fire from water. Again, a person would be standing on some insulating pedestal, would hold one of his hands on that electrifying machine that somebody else would keep spinning, and then this person would have a saber, and then there's this lady here who has in her hand a little phial with alcohol or water, and when that person approached the saber and approached the surface of the water, a spark would come, and that spark might even start a fire if this is alcohol or some other inflammable substance. So very much an amusement. And the amusement reached most of the continent and even very remote places. And our next hero, a very important one actually, Ewald von Kleist, he lived in a very remote village in, back then, Prussia, modern-day Poland, Kamien-Pomorski, by the Baltic coast. And he was there, the dean of the cathedral in that city. And again, he also played with electricity. He heard, obviously, about these marvelous things that were happening in the living rooms of the rich, and he wanted to experiment with them himself and reproduce some of them. Now, in fact, as will be important later, he studied jurisprudence. He was a lawyer by profession. He studied in the Netherlands at the University of Leiden. And so what he did is the following. October 11th, 1745, he writes, "If a nail or a strong wire is introduced," up here is his original drawing, "into a narrow-necked little medicine bottle, and the nail is subsequently electrified, especially powerful effects follow. Everything works better if a little mercury or alcohol is placed inside the medicine bottle." Okay, so here you can imagine how he must have charged his vial. He holds it in his hands with the nail sticking out, and the nail is connected to whatever electrifying machine he was using. And he found that if he electrifies that nail strongly, he can take that bottle and carry it into another room and then ignite spirit of wine over there, or turpentine. Okay, this was remarkable to him because this was the first time he had something that he could actually walk around with and simply store electricity and then use it over there without having to have a piece of wire connecting those far apart distances. And so he was convinced that he had found something new that people didn't know about, and he wrote a letter to 5 people he trusted. Okay, these were people who were at universities, scientists, respectable people. And he got word from some of them, Lieber Kuhn from Berlin, who was one of the people he wrote to, and he called it novel and remarkable. Right? So indeed, he had found something that nobody else knew about before. But unfortunately, nobody really managed to repeat his experiments. Nobody managed to pull off that thing he wrote about in his letter, which is to electrify that nail in the bottle and carry the bottle over there and then electrify wine, spirit, or turpentine in a different room. So why couldn't they? What happened? Well, remember that Dufay's rule was very much present in everybody's minds, which is that if you want to electrify something, that something had better be placed on a glass plate, so that otherwise it wouldn't work. Remember, Dufay said if you use wood, you would try in vain. Now, if you look carefully at that picture of how he charged the glass, or how he charged the nail that stuck into his medicine bottle, he was holding it in his hands. He was doing the exact opposite of what Dufay was prescribing. But he didn't specify that in the letter that he wrote. And obviously, everybody he sent this letter to, reputable people who knew the state of science, they would imagine that he charged his nail by putting that glass medicine bottle on a glass base instead of simply holding it in his hand. And so that's what they did, but they couldn't repeat the experiment. So if they put that glass vial on a glass base and then electrify it, nothing would happen. And that extremely powerful charge of electricity that he managed to produce would not appear. And in fact, today we know, but von Kleist didn't know and nobody else knew at that time, that is precisely the crux. By holding that glass vial in your hands, what would happen is that the vitreous electricity, the positive electricity from the electrified glass, would go through the nail towards the inside of that bottle, but by holding it in his hand, an equal amount of negative resonance electricity would come through his body and sit on the outside of the glass. And that confluence of positive and negative electricity would be the secret behind that extremely strong and sort of durable way of storing electricity. And so because nobody could repeat his experiments, today his name is not really well known and is not associated to that important discovery that he had made. But it wouldn't take long before other people independently rediscovered that same effect. And one of them actually was at Leiden University, that place he had studied a long time ago, and that person was Peter von Maschenbroek. And he was one of the first to run into this by accident independently of von Kleist, and he would be, again, one of the first people to be receiving a serious electrical shock. One of the first people in history, and here is what he writes about receiving that electrical shock. I would like to tell you about a new but terrible experiment, which I advise you never to try yourself, nor would I, who have experienced it and survived by the grace of God, do it again for all the kingdom of France. He was really impressed by whatever he had done, accidentally. Okay, so suddenly, electricity went from something that is amusing and a party trick to something that imparts terror on people. But all they had to do was, instead of putting that glass vial or that subject that is to be electrified on an insulating base, they simply had to hold it in their hands. Imagine how they must have felt. Something as innocent and inconspicuous as a change as that led to such dramatically different outcomes. And remember, people didn't know what electricity was doing or how it was or how to tame it. So, imagine if a simple change like that led to something as dramatic and dangerous, who knows what else might be possible with that electricity, right? If you don't know what you're up against, what should you do? But in fact, this was a serious blow to the understanding back then. I mean, Dufay's rule certainly now doesn't make any sense anymore. This was exactly the opposite of what you would expect. But people were hesitant at abandoning Dufay's rule entirely. And in fact, they said, no one ever thought that the rule of Dufay must allow an exception in the case of glass. Okay, so they tried to hold on to Dufay's rule. We talked last time about paradigms and such. So this was clearly a case where people tried to preserve that paradigm by adding an exception. Okay, Dufay's rule is valid for everything except for glass. So if you want to electrify a nail in a glass vial, Dufay's rule doesn't apply and you better hold it in your hand as opposed to placing it on a glass base. But very soon, people jumped over their own shadows and they continued experimenting with what then became known as the Leyden jar, that first durable way of storing electricity. And people tried improving it. They put metal foil outside, on the inside there is still the nail that you use to electrify it. And today we know that the way it works is that there is an equal amount of positive and negative electricity on the outside and the inside, but again, back then people didn't know. We'll see in a second how they figured it out. And they would connect many such Leyden jars together in what they would call a battery. Okay, a battery in the sense of an arrangement of many simple, similar objects, storing a large amount of electricity. And many people did experiments with them, among them Ben Franklin. Okay, so in 1750, he was also one of those people who gets a shock the first time he plays with it. 2 nights ago, being about to kill a turkey by the shock from 2 large glass jars, I inadvertently took the hole through my own arms. The one who does the operation must be very aware lest it happen to him to mortify his own flesh instead of that of his hen. And so, steadily, people again began integrating that Leyden jar once they understood what happened into their party amusement tricks. Okay? So you can see this person here holding a Leyden jar being connected on one side to that electrifying machine, on the other side through that rod, and they would receive an electrical shock. But they discovered, effectively, what today we call an electrical circuit. That if that overall line that closes that circuit is longer, because there is a second person through which the electricity has to pass, the shock they would receive is a lot less severe than in that blue case where the circuit the electricity has to complete is a lot shorter. In fact, they pushed it to the very limits, and what they call the discharge train, where many people, here's an example from Japan, many people would hold hands, you see, in a closed circle, and everybody would get electrified sort of simultaneously as they discharged the Leyden jar. But there is still utter confusion at this point of how the thing actually works. While the bottle charges, electrical ether accumulates in the water and, by seeping through the glass, in the bottom of the jar. These accumulations set up local peaceful double fluxes. I don't know what that means. And in fact, it was again Ben Franklin who finally figured out why the Leyden jar was so powerful. And he was the first, by the way, to whom we owe that positive and negative nomenclature instead of that more cumbersome vitreous and resinous one of Dufay, because Franklin writes,
At the same time that the wire at the top of the bottle is electrized positively, or plus, the bottom of the bottle is electrized negatively, or minus, in exact proportion. And here's a wonderfully ingenious experiment that he did to demonstrate that in fact that was the case. Okay, so he takes a Leyden jar, he charges it up, and after charging it, he puts it on an insulating pedestal. Okay, by this he ensures that once the jar is charged, no electricity can flow anymore out or in, okay, through that insulating pedestal. And what he does then is he takes a piece of cork and he suspends it from an insulating thin silk thread. And what then he does is he moves it back and forth between the inner surface, the nail that's being positively charged, and the outer surface that's, according to him, contains an equal amount of negative electricity. And so as he brings that cork in contact with the positive side, the cork picks up some positive charge. He then moves the cork over to the other side, where it deposits that positive charge and sort of annihilates some of that negative charge that's sitting there, but at the same time picks up some negative charge, and then he moves it back where the negative charge is deposited and more positive charge picked up and so forth. And as he puts it back and forth, he manages to discharge the entire Leyden jar. Okay, but he says, look, I've just managed to discharge it only by ferrying electricity back and forth between the two sides of my jar, but nothing could come out and nothing could go in because everything else is insulated. And that shows that there is no overall electrical charge in my Leyden jar, but there's just a separation into positive and negative, and that's why it works. And the electricity fully disappears at the end. And so this is very much what we have today. The statement is, you can only really charge a Leyden jar, which today we would call a capacitor, if both of those terminals are really connected. Okay, so we saw von Kleist connected both inadvertently by holding it in his hands, as opposed to following Dufay's doctrine and putting it on a glass base. And today that's, if you will, manifest. If you open up some electrical appliance, you will see many of these, which are electrical capacitors, and all of them have two wires coming out. And if you want them to work, you need to connect both wires. If you just connect one, it will not work. Ben Franklin also made up his mind as to what the nature of electricity was. Okay, centered around his understanding of there being positive and negative electricity. And he says electricity works in the following way. There is common matter, and there is electrical matter. Okay, common matter is the thing that material bodies are made from, this table, for example. And if you have two blocks of common matter, they would be attracting each other. On the other hand, electrical matter is some sort of subtle fluid, like a gas, that is repulsive. Okay, it mutually repels and tries to spread out as much as it can. Okay, again, there is this old doctrine of caloric lingering here. And then what we see around us is neither of the two, but in fact is neutral matter that doesn't have any electrical charge. And that is simply made up by common matter and electrical matter put together. Okay, because the two of them, they attract very, very strongly. And so if you have a piece of pure common matter, the electricity will rush into it and sort of fill it out to the maximum degree. And then he says, if you charge up something to give it some overall electricity, what happens is that there is a surplus amount of electrical matter in that body, and that surplus amount would form, if you will, a little atmosphere on the surface of that object. Okay, this blue thing here. And then what happens is that because common matter attracts, but electrical matter repels, two neutral bodies that have sort of the correct amount of both, they do not attract nor repel. But if you have two charged objects that have each a surplus amount of electrical matter, they would now repel. Because the electrical matter repels, and there is some excess amount, and that excess amount leads to that repulsion. So fine, so good. But also Franklin noticed that this does not explain at all why it repels. And he was worried, in fact, about that action as a distance, just as we saw before. It seems absurd, he writes, to suppose that a body can act where the body is not. I have no idea of bodies at a distance attracting or repelling one another without the assistance of some medium, though I know not what that medium is, nor how it operates. In fact, there is a more serious problem with Franklin's theory, which is, since Dufay, we know that also negatively charged electrical bodies would repel. Now, in his scheme, a negatively charged body is one that has a lack of electrical matter, not a surplus. But in this scheme, they would not repel. If there is not enough electrical matter, it would be the common matter that's attractive that would have the upper hand and would actually attract and not repel. Franklin was certainly aware of this, but we don't know what he tried to think in terms of how to get out of this conundrum. Okay, his theory was simply not working. And so things were still very confusing. In fact, they're going to get more confusing. And this is now the time when we come to Luigi Galvani, who we already met on the very, very first lecture, who is an anatomist, so a physician, in Italy at Bologna. And what he cared about is what today we call comparative anatomy. Okay, he would compare the physiology and the skeletons of different species to learn about what things are common and what things are different and how they might relate. And so it wasn't surprising, perhaps, when in 1791, he suspended a prepared frog from his railing that surrounded the roof garden he had at his house. So he writes, prepared frogs, which were fastened by brass hooks in their spinal cord to an iron railing, which surrounded a certain hanging garden of my house. And as he sat there, he would watch the frogs falling into contractions. Their muscles would twitch. And at first he thought that this is something to do with sort of lightning and storms, but in fact, as he watched more carefully, these contractions also appeared when the weather was good and there was no storm and no rain. And he was intrigued by this, and he continued by doing more controlled experiments. He took the frog inside his house and puts it on the table. When I brought the animal into a closed room, placed it again on an iron plate, and began to press the hook with which it was fastened in the spinal cord against the plate, behold, the same contractions occurred as before. Okay, so this is something that's not by chance. He manages to reproduce it and excite it as his will. There is the iron plate, and there is the brass hook that's connected to the spinal cord of the frog, and as he closed, if you will, that circuit, and pressed the hook against the plate, the frog would twitch. Today we would call it the frog is galvanized, it springs into action, and that's in fact where the term comes from Galvani. I immediately repeated the experiment in different places with different metals. Okay, he has a hunch that maybe the metals are important. The results were the same, except that the contractions varied with the metals used. That is, they were more violent with some and weaker with others. Okay, so something has to do with the metals here. No muscular contractions or movements were evident when using a non-conductor over a poor conductor like glass, gum, resin, and stones. So it clearly had to do with the metal being metal and therefore, as we know from Stephen Gray, being conductors. If he uses non-metals or poor conductors, nothing happens. So his conclusions, 1791, were the following. Well, he was greatly surprised, and he was led to suspect that electricity was somehow inherent in the animal itself. So he puts the frog front and center. He says the frog is the one that gives the electricity, and that the wire around it is simply, as we know, necessary to close the electrical circuit, and once its circuit is closed, the frog will spring into action. An observation that is a kind of a circuit of a delicate nerve fluid that's made from the nerves of the muscles when the phenomenon of the contraction is produced, similar to the electric circuit which is completed in a Leyden jar. Okay, he was living in this contemporary world where people knew about Leyden jars, they knew about electrical circuits, and they knew when electrical circuits were closed, things would happen. Very likely, the same is happening here. That's what he called animal electricity. The source, the frog is the source of electricity, and the wiring, the metals, is just to complete the circuit. In fact, people already back then knew that there were, in fact, animals that could produce electricity to defend against their predators. But, he missed one giant hint, and that is that the contractions varied with the metals used. And he, in fact, wrote about this. So if it was really just the closure of the electrical circuit that was the job of the metals, then the dependency on which metals were used wouldn't really matter too much. But he noticed that it does, but he decided to ignore it. And that opened him up to an opposition by Alessandro Volta, who we have also already met. And he writes a letter not only 2 years after Galvani published his findings, and he says, "The name of animal electricity is by no means proper in the sense intended by Galvani." Okay, he picks up on that hint. No, he says, this is mere artificial electricity induced by some external cause, excited originally in a manner hitherto unknown by the connection of metals with any kind of wet substance. Okay, he says, whatever your frog is doing is nothing central. The frog is simply some wet substance that you need to connect two metals, two different metals. And he proceeds to give a proof. Okay, in a letter, again, sent to the Royal Society in England in 1800, he gives a demonstration that in fact you don't need any frogs to have that same phenomenon. You can do the following. The apparatus to which I allude, and which will, no doubt, astonish you, is only the assemblage of a good number of good conductors of different kinds, different metals, arranged in a certain manner. So here's what he does. 30, 40, 60 or more pieces of copper applied each to a piece of zinc, and as many pieces of pasteboard well soaked in water, such interposed between every pair of two different metals in an alternate series. Okay, so here's what he does. He takes two different metals, which in his case were zinc and copper, cuts them into discs, stacks the discs, and puts some wet substance in between, which he doesn't use frogs to do, but he simply uses pasteboard that he soaks in water. And then he gets this column, and then he continues, and this is really all that's necessary for constituting my new instrument, which, as I have said, imitates the effects of the Leyden flasks. Okay, so here he has something that is very easy to make, and that everybody who reads his papers can simply reproduce, and it would do the exact same thing as a Leyden jar. It would be a positive side and it would be a negative side. So this apparatus, much more similar to the natural electrical organ of the electric eel that we saw before, much more similar to that than to the Leyden flask, and therefore to electric batteries, which are just arrangements of Leyden jars at this point, I would wish to give the name of the artificial electric organ. Okay, he says this is clearly something that resembles electricity, but he is not sure whether it's the same electricity as the one in the Leyden jars, because there's clearly also differences between them. And it is his, what we would call today a battery, that James Joule in 1840 used to do some of his experiments. He writes about voltaic electricity. Voltaic electricity specifically referring to that kind that comes out of Walter's piles. And that is really the first steady-state source of electricity that was very, very important for many things. You can imagine a Leyden jar, if you charge it, it would be discharged in an instant, whereas Walter's voltaic electricity would be supplied steadily and could be kept up for many hours. And of course, this is exactly what today we call a battery, and it works according to the exact same principle, and it's still a very convenient source of electricity. So we have arrived in the 1800s. And the state of electricity then is still a pretty confusing one. We've seen how people knew how to generate ordinary electricity by rubbing glass spheres. We've heard about voltaic electricity, and we've heard about animal electricity. Because what Walter missed was in fact also obvious, which is that there is really something that is animal electricity. There are really electric eels that produce it, just frogs don't. So people knew a couple of different sources of electricity, but people didn't really know what it was made of. Remember Hawksby's electric spider webs that sort of miraculously behind the scenes pulled up the woolen threads. Imagine two-phase vitreous and resonance electricity that have nothing whatsoever to do with them. They're exactly opposite. There is Ben Franklin, who shows that sometimes both of those electricities can be present at the same time in the Leyden flask, but also his understanding of what was happening was exactly beside the point. And then we have the first, if you will, technological application of electricity, the Leyden jar, to store more electricity and to amplify it, as people call it then. And people could also now transmit electricity, since Stephen Gray. So still, things are very confusing, and in fact, before they get better, they will get even more confusing. But this is something we'll keep for next week. Thanks a lot. Questions? Yes?
Back with the magnet with the Chinese, the little magnetic fish, you mentioned that it was used in divination. Was that little fish vibrating back and forth because of the fluctuations in the Earth's magnetic field?
So I don't know exactly what the procedure was that they used, but it was most definitely not due to fluctuations of the magnetic field, but simply by placing that magnetic fish somehow on the plate, and then it will go through some process of settling down, and that process of settling down would be very random because it depended exactly on how you placed it on and so forth. My best guess is that they used that settling down process of reading off, the lettering that surrounds it, and use that, if you will, as an input to their divinations. Yes?
I'm very interested in when the concept of action and resistance became known, and you said that it sort of first presented itself in the investigation of electricity around 1600, but why wouldn't it have come up in the investigations of magnetism, which was much earlier?
With that's right. It's true. Magnetism would also have had that, would also give people that exact opportunity to discuss it. And maybe people already had some idea about magnetism and action at a distance. I could presume they did. With magnetism, it was, at least in the context of navigation, maybe a bit less obvious because there was no other magnet until people discovered that the Earth was a magnet. Okay, so if you had a compass, the needle would somehow magically arrange itself, but there wouldn't be a clear mechanism according to which that would happen, unless you already know that the Earth is the second sort of interacting object. But it's true. As you say, if you take two magnets, and probably people did, or two magnetites, two pieces of lodestone, and you put them together, you would feel the force. And that would certainly have sparked the same thoughts. Yes?
All right, now you're in the mid to late 1700s already, right?
So here, this is still 1600.
No. Your talk today is gone up, okay.
So at the end we were, close to the early 1800s, or the very late 1700s.
Okay, but
Yes.
by then, Newton had described laws of gravity, right? So
Yes, and Newton was also very confused about why there is action at a distance. I mean, as you say, with gravity there is again the same problem. Clearly, the Earth revolves around the Sun and the Moon revolves around the Earth, and since Newton's days, people knew that there was some universal force that keeps the Moon in place. But by saying that there is a force acting on the Moon, you're just describing it, but you're not explaining the mechanism that gives rise to the force. And so very much in Newton's case, there was also this action at a distance. There is no discernible medium that connects that force from the Earth to the Moon. So also there is the same problem. And then Newton didn't have an answer to that problem. And as we'll see in the case of electricity, it would be many more years before people truly understand or truly have an explanation of sorts for why there isn't fundamentally an action at a distance, but why there is actually something that transmits that force, but it's not visible to the eye, and it's in fact very invisible even to very specific instruments. And that's another good point. Notice, by the end of today, notice the complete absence of instruments. Electricity was something so stark and so striking that all of those investigations really, they only concerned effects that were sort of visible to the naked eye. People got electrical shocks, people touched each other and got electric shocks and so forth. This is the input, if you will, the sensory input that people had to describe and study electricity, but there is no instrumentation of any serious kind at this point. And if you remember from the study of heat last time, it was really the emergence of precise thermometers that then led to the big breakthroughs in understanding. And we'll see the same thing happen next time. Next time is when instrumentation will come up, and that will give people a much deeper insight into the nature of electricity. Yes?
There was a story about a Greek shepherd, Magnus, who went out in the field and first noticed that his rod actually stuck to a rock. I think in Greece, there's some story about that, but that one metal, as you said, will kind of impart whatever it was to something else. And I think that you mentioned the role of heat, that by heating certain materials, that it would also lose this type of attraction. But here's the interesting thing. You mentioned Benjamin Franklin, and then you mentioned about the role of conductivity. I think everybody kind of knows in the world that the lightning rod was a very important invention by him. In fact, people at that time were concerned about conflagrations of cities based upon lightning as, I guess you could say, with storms. And he realized the importance of actually having
Right.
a device to deal with that situation. But the thing is, all this was basically done with
So that's a very important question. So the question is, maybe if I go back here, what action at a distance has...
Because all this is based upon things attracting other things.
Yes.
Or things causing other things to move. The very nature of physics. Trying to understand why this thing here and that thing there moves without anybody pushing.
Right. And that's right. So that's what, at its heart, action at a distance is, right? If I put something here, the other thing over there moves.
Yeah, what makes it limited?
Exactly, and it's not clear, right? It's not clear. And it's equally unclear in the case of electricity as it is in the case of gravity, that Newton was very confused by. But already people back then understood that, at least since Ben Franklin's days, there is, if you will, two different states in which electricity can exist. It can exist in that, if you will, static state where nothing flows, in a sense, nothing is passing from one object to the other, but, there's just action at a distance. Compare that to Ben Franklin's lightning rod, when there is very clearly something passing. You can see it, right, from heaven down through the lightning rod. Okay, that's, if you will, the second state of electricity. That's electricity in motion, as people called it then. Whereas this is sort of, electricity in its static form where nothing moves. The electricity doesn't move. But even electricity in a static form would have that subtle effect of action at a distance.
Yeah, but again, it gives rise to the fact that with magnets, they also saw a bipolar.
Yes. Yes.
Attraction.
Precisely. And
Was this also discovery of magnets behaving this way, formed the foundation or basis of looking at other materials with electricity, and that the connection between electricity and magnetism may have
yes, very excellent point. So there is a very deep connection between electricity and magnetism, and we're going to see some of that play out next time. People recognize the many great similarities between magnets and electricity. Magnets can repel and attract depending on how you orient them. Electricity, since two-phase days, we can use to attract and repel things. But there were also important differences, and as we will see next time, that also led to a lot of confusion as to what the exact nature of magnetism was. And in fact, we'll see that magnetism and electricity are deeply related, and you can use one to generate the other, and you can use the other to generate the first one. And in fact, let me mention one more thing, because he pointed out what Gilbert wrote about sort of having to heat objects to electrify them before rubbing them. In fact, heating them, today we know, Gilbert didn't know, but heating them simply had the effect of dispelling moisture that accumulated in the body. And the moisture would sort of have the effect of attracting that effluvium that's being given out, that the understanding went in these days, from the electrified body. And that if that effluvium was sort of captured by the moisture, the body would simply not be electrical anymore. So to dispel the moisture was a way, in those understanding of in these days, to simply get rid of the electricity capturing moisture. Now, people already knew that even then, on a rainy day, this rubbing a glass rod didn't really work as well as on a dry summer day. For the exact reason, as we know today, understand, on a rainy day the humidity of the air is a lot stronger, and that has the effect. Today we know it simply conducts electricity away, right? So it makes the electricity, it contacts, it would, that's right. So it would simply, make the electricity flow out of the body that you're trying to electrify, and that's why it wouldn't become electrical. Back in the old days, people had it exactly backwards. They said the moisture in the air would prevent the electricity from getting out of the body, and that's why it wouldn't appear to be electrical, right? But sort of the story goes in exactly the opposite. My pleasure. Yes?
This all seems to relate to the discovery or establishment of the law of conservation of energy, both with the steam engines and with the
Yes.
electricity.
Yes.
Are you going to be focusing on that point, or can you give us anything concerning that conservation law?
Excellent question. Yes. The best place to talk about the conservation of energy in general would have actually been at the end of last lecture, when we then ran out of time. So maybe we can have a bit of a discussion now. So the emergence of the emergence of the understanding that there is something that is conserved actually is something that then went on top of the caloric theory of heat. If you think back to what Sadi Carnot's explanation was why heat engines work, is they simply do nothing but they use caloric that flows from a hot side of the machine to the cold side of the machine, but there would be no loss of the caloric. It would simply be flowing like water, down a waterfall from hot to cold. Now today we know that if you replace caloric in Sadi Carnot's theory with heat, then it's almost exactly true, except that there is a small amount of mechanical energy that the heat engine produces. So the amount of heat, in today's understanding, that flows into the cold side is actually a bit less than the amount of heat that flows into the machine from the hot side, the difference being exactly equivalent to the mechanical energy that the machine produces. Okay, so that equivalence between mechanical energy and heat was James Joule's big accomplishment. Now, you can ask, okay, fine, why did people not notice that that was the case? Right? So why was Sadi Carnot, who was still operating in that doctrine of caloric, in which caloric was really indestructible, and caloric, if you will, was also conserved. You could not create it, you could not destroy it, you could simply make it move from one side to the other, right? It was conservation of caloric. Why did people not realize back then that the conservation of caloric was not true, and in fact conservation of energy was true? Well, it was simply because the steam engines in those days were so inefficient. Okay, so the amount of mechanical energy that comes out here would really lead to a slightly less amount of heat being emitted down the cold side, but that difference was so imperceptible because the machine was so inefficient. That's why, to first order, if you will, conservation of caloric works fine, right? Because the efficiency of these machines was below 10%, right? So to within a few percent, conservation of caloric is perfectly fine. If you start to really do precision measurements, if you will notice that caloric is in fact not conserved, and that something else then takes the role of caloric, and today we know that as the conservation of energy. And to a very large degree, James Joule did exactly that. He showed that there is a way to translate between electrical energy or the mechanical energy of his weights dropping down and heat. Okay, that is exactly that statement of conservation of energy, that you can turn it from one form into another form, but the overall amount of energy doesn't change. It simply takes on a different form. Very good question. Yes?
The speaker last year mentioned that there was a great deal of heat shortly after the Big Bang.
Yes.
And I asked him, well, what happened? And then it cooled down. I asked him, well, what happened to the heat? Where did it go? He didn't give me a full answer. He says, well, it was electromagnetic, blah, blah, blah. He didn't spend much time on it. But can it be said that once heat is created, it always exists somewhere. Heat is lost to cooler objects, it's transferred, but then they are slightly heated somewhat. So, can it be said that heat, once it's created, exists somewhere?
Excellent question. So the question is, for the recording, once you create heat, okay, in James Joule's ways or in any other way, and you just leave it be, okay, what happens to the heat? And, well, we know today for a fact that once you generate heat, it doesn't always remain as heat, right? So this is the counterexample. If you have a boiler that heats up steam, you generate heat, you can use some of that heat to do mechanical work again, right? You can convert heat back to mechanical energy, while you can also use mechanical energy to produce heat, we know from James Joule. Now, the big sort of conclusion by Sadi Carnot was that it's very easy to fully 100% dissipate mechanical energy to generate heat. Okay, you just need to rub your hands. It's a lot harder, and in fact impossible, to go the other way, to take 100% of the heat and convert it back into mechanical work. That doesn't work. There is an upper limit to how efficient you can turn heat back into a more ordered form, if you will, of energy that is mechanical work. Okay, now if I understood your question correctly, you were asking, if you have heat and you don't attempt to run it through a heat engine, but you just leave it there, what happens to the heat? And the answer to that is that it would try to maximally disperse itself and to maximally dissipate outwards until we get to that equilibrium that Joseph Black already mentioned, when the thing stops, when everything is exactly at the same temperature. Okay, at this point there is no hotter or cooler anymore, and at this point there is no direction anymore in which heat could flow, right? Because heat flows from hot to cold, and if there is nothing that's hotter or colder than anything else, the heat flow would stop. Okay, so according to Joseph Black, that's the ultimate end product of what heat does if left to its own devices. And in fact, since you bring the universe, there is that idea of the heat death of the universe, which you can imagine in exactly the same terms. Joseph Black mentioned that room without windows, and irrespective of which objects you place into it, at equilibrium, if you wait for a sufficiently long amount of time, everything will have the same temperature. Now replace that with the universe, which is also a room without windows in a sense. And today we have things that are hot and cold. There is the sun that's much hotter than the earth, and then the outer space is much colder than the earth and such. So today there is still a great imbalance in temperatures in the universe, just as it was in Joseph Black's room when he put like a hot mug of coffee and a cold stone into it. But the same principle holds. If you just imagine, we fast forward into the future of the universe, at some point there will not be any more places that are hotter or colder. And the entire universe is going to be a structureless, featureless mess of exactly the same temperature. And then everything stops. Nothing moves anymore. And that's the ultimate fate of the universe. And this is what happens to heat.
I didn't mean to get us there, but will you, just briefly, next time, will you give us a definition or an explanation of magnetism?
Yes.
Do we know? Do we know?
Yes, we do. Today we know. And next time we'll see how people came to study magnetism with the same vigor as they studied electricity. Yes. Okay, thanks a lot. See you next week.